All right, so let's go ahead and go through the midterm review. So what we're going to do in two parts in this midterm review. The first part is we're going to go through a data path review, and then we're going to do a bunch of sample problems from previous exams. So no, don't look ahead in the handout because in these three steps here, you're going to find the answers for each step are after them so that you can do the next part. So don't skip ahead. We're going to start out listing all the parts of the data path. Then you're going to add all the inputs and outputs, and then we're going to connect everything up so you'll have built the full data path. So let's go ahead and get started. First, list all the parts of the data path. Go ahead, pause the video, and answer this together with your partner. Okay, so let's take a look at this. Here are the parts that we have in the data path. So the ALU is probably pretty easy to remember because that's what does all the work. And then if you think about where the information comes from, it comes from the register file. So those are easy to remember. You've also got the data memory if you want to store stuff. And then you've got the instruction memory. And if you remember, the instruction memory is what the PC feeds into, so it tells us what instruction to get. The other parts are a little harder to remember. So the sign extender, if you think about the add immediate instructions, you've got that in there. Then we've got these other adders up here and this shifter. And this is for the branching, for the next PC and doing branches. And then of course, we've got the control logic. So those are the parts that I had in the data path. All right, now let's go on to the next part. So add all the inputs and outputs for each of them, but don't connect them up yet. So go ahead, pause the video, solve this together with your partner. All right, so here are all the inputs and outputs for everything. So the PC takes in the next PC and outputs the current PC. This adder obviously takes in two things, one of which is going to be 4 because it's always PC plus 4 and then produces a result. The instruction memory has an address of the instruction to read and it outputs the instruction. The register file is really the complicated one because it has to be able to select which two registers you read, the read registers, as well as output the data for them. But it also has to be able to do a write. And so when you write, you need to tell it which register to write to and what data to write, and you need a control signal which specifies whether you're actually writing. Sign extender is pretty simple, takes in 16 bits, outputs 32. The ALU has two inputs here, and I've shown the mux that we'll use later, and then it has a bunch of outputs. So it has the result of the output. It also has the 0 output, which we use for branches, and it has a control to tell it what operation to do. The adder for the branch up here, well, it just has 2 inputs and an output. The memory takes an address and data to write, and it takes control signals saying whether you're reading or writing. So we need to know whether we use this to write or we read it. If we're reading, it has the output value that it writes out. Then we've got some muxes in here. So this mux selects which one of the sources we're going to use, and this mux selects whether we're going to take data from the ALU or from the memory and write it into the register file. Okay, next step, go ahead and connect everything up. So pause the video, answer this together with your partner. Okay, so here's everything connected up. Let's take a look first at how the PC flows through it. So we have our current PC, sorry, next PC gets stored in here, and it comes out as our next PC on after the clock cycle. Then it's a memory is going to send, the instruction memory is going to send out the instruction. Parts of it are going to control which registers we access. Parts of it are going to go to the sign extender. This is going to then flow through. The outputs from the register file are going to go into our ALU. One of them goes directly. The other input to the ALU can either select the output from the register file or the sign extended value, depending on whether it's an I-type instruction. The result of the ALU then goes into the address of the memory, if you want to calculate the address, or it bypasses it and goes to this mux if you're going to write it back into the register file for R-type instructions. The memory itself takes in an address and takes in data, and the data comes directly from one of the register files here, and the results of it go into this mux, which selects whether it's the result of the memory or the result from the ALU that gets written back into the register file. Up here for the next PC, we have the shifting of the sign extended value, which we then add to PC plus 4. This is if we're doing a conditional branch. And then we have a mux here, which selects which do we do. Do we do the conditional branch or do we do PC plus 4? All of the blue signals here are going to come to the control, and the control is going to tell them what to do. We also need an output from the instruction going into the control to tell the control how to interpret the instruction. Okay, so let's take a look at how this all works. So we have our next PC waiting here, calculated from our previous instruction. When the clock signal comes in, we save that in this latch, and it comes out the other end. When it comes out here, it then goes into the instruction memory. The instruction memory loads the instruction, which it then sends in to select which registers to you and what the sign extension value should be. It's also going to go to the control from here. The register file then reads and outputs the value. So we're doing add I here. So we want one value from the register file and one from the sign extension. So we'll take one value from there, and then we take the sign extension value, and the control is going to set the ALU source so that we take that value. Now at our ALU, we've got one register file and one immediate. The ALU operation is going to be plus, because it's add I, and then we're going to generate our result. Now mem to reg is going to select taking the result from the ALU because we're not doing a memory operation. So it's going to take that value and it's going to bring it back to the right register file. Now the right register here is going to be selected from add I, from one of the register operands, and the control is going to set register write to true because we want to write the value back in. So now we have our new value sitting here waiting to be written. At the same time, we're going to calculate the next instruction. So we take our current PC, we add 4 to it, and then this is going to be set up as our next PC because we're not doing a branch. So we're not going to choose the other input here. Now we've got our new PC ready, and we've got our new data for the register file. And what happens next is the clock comes in. When the clock comes in, we update our next PC to our current PC, and we take this data we have sitting ready for the register file, and we write it into the register file. So now we've updated the register file value. After that, we start over again. Now we've got our current new PC, and we're going to go through the whole thing, and our register file has been updated. So that's how the data path works. All right, now we're going to go through and do some reviews of some questions about the course, or about the material we've done so far in the course. So the first one here is about the PC register. So go ahead, read the question, answer it first on your own, then after you both answer it, discuss it with your partner, then continue the video. Okay, so let's take a look at this question. Can you use the PC register for read, writing, and math? Okay, so the PC register, well, it holds a 32-bit value, it holds the PC, but it's a little tricky because you can't just load and store to it or use it in instructions. However, you can do some stuff with it. So this answer here is somewhat. You can access it, but not easily. So how can you access it? Well, you can change what's in the PC on a jump or branch, and you can store to it and read from it with jump register and jump and link. Those both allow you to put values into it, but it's really hard to control what those are. So you could imagine writing a really weird program where you actually controlled it this way, but it's not a standard thing to do. So the point of this question is it's not a regular register that you can use as easily as others, but you can control what's in it by these different instructions. All right, go ahead for the next one. Pause the video, answer the question first on your own, then discuss your answers with your partner. Okay, so what's the basis of this question? So this question is asking about memory locations and register files. And the tricky part about this question is to remember the register file holds 32 words, whereas memory locations hold bytes. So you need to convert between words and bytes, and there's something about 32 versus 31. So we need to remember that R0 can't store data. So if we do that, we can do the math. We can say each register file, the register file holds 31 words, not counting R0 because it's always 0. Each word is 4 bytes, and a memory is byte addressed, so 31 times 4, 124 memory locations to fill the register file. All right, go ahead, pause the video, answer first on your own, then discuss with your partners. Okay, so the question here is how much space do branch labels, like skip that you write in your assembly, take up in the compiled code? And the answer here is none. And the reason for that is if you think about what a branch does, a branch just says offset by some amount. So the branch just says go to some place. Now where do you go? That's from the label. So the label skip, for example, if it's 4 instructions after a branch, when you assemble your code, it will change that branch to just say 4 instructions ahead. So these skips don't actually show up in the code. Remember how we showed how branches were encoded? They had instruction offsets. So there's no encoding of the labels in the actual programs. They're just used to help you as the human write the code. All right, let's move on to ISA 2. So go ahead, pause the video, answer the question first on your own, then discuss with your partner. Okay, so in this problem, we're adding a new instruction, and the instruction is branch not equal immediate, register constant address. So the idea is saying, can we take a register, compare it to a constant, and if it's not equal, then we go ahead and branch. So this allows us to compare, is register 37 or something like that. And the question here is how can we use the bits in our register encoding, in our instruction encoding effectively? So if we have an 11-bit constant, how far can the branch jump? So if we take a look at our encoding here, we have for I format instruction 16 bits, and we can take away one of the registers. So we only need one register now for this because we only need to encode one register. So that means we have this many bits, 21 bits, that we can use to encode stuff. We're using 11 bits for the constant, so we have 10 bits left for the branch. Okay, now if we have 10 bits left for the branch, the question is how far does that get us? Well, 2 to the 10 is 1024, but we interpret this as a 2's complement, so that means we can go plus 512 or minus 512. So we have 21 bits, we have one register, gives us 10 bits for the address. The address is 2's complement instruction offset. So remember, this isn't bytes in addresses, this is instructions. So that gives us 512 plus or 512 minus instructions. All right, you know the drill. Okay, so here we are, we're going to add a load big constant to register instructions to MIPS. This is going to use a modified I format encoding, and the question is how much does this speed up loading a 32-bit immediate? Well, the trick about this question is if we have a modified I format encoding that only needs one register, that means we have more bits to store the immediate. So we should be able to load more bits at a time, and the question is how quickly can we load all 32? And the answer to this is no faster. And the reason for this is because we have 16 bits and we can use another 5 bits. So we get the same 21 bits we had in the previous previous problem, but we still need 32 bits. So even though we got 21 bits all at once, we still need 2 instructions to get all 32 bits. So it's no faster than if we could just load 16, which also just needs 2 instructions. All right, go ahead, pause the video, answer the question first on your own, then discuss with your partner. All right, so what size adder do we need to include the immediate into the next PC for a jump instruction? So the question here is getting at how, when you do a jump, do you merge with the next PC? The answer is you don't need an adder here, because in the jump instruction, you just replace 26 bits. So you take the PC plus 4 and you just replace 26 bits. So we don't need to include any more adders to include this. We just need to replace those bits. All right, let's go on to arithmetic. Go ahead, pause the video, answer the question first on your own, then discuss with your partner. Okay, so we've got a problem here. We want to have a digital scale that can measure up to 2 kilograms with an accuracy of 0.01 kilograms. And the question is, how many bits do you need for this? So the answer is 8 bits. And the reason for this is if you look at how much information here. So to cover this range from 2 kilograms to 0.01 kilogram increments, you need 200 numbers. Okay, well, if we need 200 numbers, we need 8 bits, because with 8 bits, we can have 256 numbers. So the tricky part here is that what that says is that each number now represents 0.01 kilograms. That allows us to represent this exactly. Because this one here is true, you can't represent 0.01 perfectly with binary numbers unless you say each binary number represents 0.01. So the trick here is to remember these are just bits. How you interpret them defines what they mean. And here, we just needed 200 of something for our scale, and it turns out that something is 0.01. All right, pause the video, answer the question first on your own, then discuss with your partner. Okay, so we're trying to make the largest positive value we can. So clearly the sign we want to be 0, so it's not negative. For the mantissa here, we're going to want to have that be as large as we can, so all ones. And then the question is, what do we do for the exponent? So we want the exponent to be as large as possible, so we multiply by the largest possible number, but the exponent is 2's complement. So the largest possible number we can have in the exponent here is going to be 0, 1, 1, or 3. So what we're going to end up with is setting those things maximum as we just described. You're going to get 0.1111 times 2 to the 0, 1, 1, which is 0.111 times 2 to the third, which gives you this value. We just shifted over by 3, and this is 7.5. All right, go ahead, pause the video, answer the question first on your own, and discuss with your partner. All right, so when you see this problem here, you should be thinking, gee, what's the way that we compute subtraction with 2's complement? And you remember that looked very familiar. It was a plus not b plus 1. And so here we've got a plus not b, but we don't have the plus 1. So what's that going to compute? Well, it's going to be a minus b, but without the plus 1, it's going to be a minus b minus 1. So this is just remembering that we saw this formula for computing 2's complement subtraction, and now we're missing the plus 1, so we're just 1 less than that. All right, let's take a look at some logic questions. So go ahead, pause the video, answer the question first on your own, then discuss with your partner. So why is DRAM so much cheaper than SRAM? Well, what costs us money? What costs us money is the size of the chip we need to make. So the reason that DRAM is going to be cheaper is because its memory cells are much smaller. So you can put more memory on the same size chip, or you can have a smaller chip with the same amount of memory. And it's just because it's smaller. Remember, excuse me, for SRAM, you need to have these active transistors that output values, and that takes up a lot of space to have a bunch of transistors. But for DRAM, you just need to have a single capacitor, and that's much smaller, so it uses up less space, so it's cheaper. Okay, next question. Go ahead, pause the video, answer it first on your own, then discuss with your partner. So now the question here is what signals we put into A and B. We've got our standard flip-flop, our two-stage latch here, and we want to store data on the falling edge of the clock. So when the clock goes from 1 to 0. Remember, before we talked about storing it on the rising edge of the clock. So how do we think about this? Well, we want to store it on the falling edge. That means when the clock is high, we want the data to come into here. And then when the clock goes low, we want the data from here to transfer to here. So we need this latch to be closed when it's high and this one to close when it's low. And so we end up with this answer here. All right, go ahead, answer the question first on your own, then discuss with your partner. So as circuits get smaller, the physical size of the DRAM cells, that is the capacitors we have, is shrinking. And as they get smaller, that means there are fewer electrons in each of those cells. So what implications does this have? We've got three possibilities here. The DRAM will become less reliable since it's harder to know if you read out a 1 or 0 because there are fewer electrons. That's true. If you have a smaller cell, you'll have fewer electrons. It'll be harder to know what you read out. The DRAM will become slower because you have to wait longer to get enough electrons out. That's true. If you have fewer electrons, there's going to be less voltage, so there'll be less forced out. And finally, the DRAM will be more sensitive to cosmic rays that leave random electrons on the chip. And that's true too, because you have fewer electrons. Every time a cosmic ray hits it, it's more likely to mess up the few electrons you have. So the answer here is all of the above. All right, let's do some questions on the data path. So I've got here in the handout an example data path for you to look at to help you with the questions. And let's go ahead and get started. Pause the video, answer the question first on your own, then discuss with your partner. So which of the following are true here? Mem to reg always selects the ALU result for R-type instructions. Well, so mem to reg is the thing that controls what writes back into the register file. And R-type instructions always write back into the register file from the ALU. So that one is true. Reg write is always true for I-type instructions. So reg write determines whether you write something into the register file. Now this might seem like it makes sense, but think about what the store word instruction does. It's an I-type instruction, but it puts its value into the data memory. It doesn't put it into the register file. PC source always selects the ALU result for I-type instructions. Well, I got to be careful here because branch not equal and branch equal are I-type instructions, and we don't select the ALU result for those. So the answer is just this one here. All right, go ahead, pause the video, answer the question first on your own, then discuss with your partner. So what are the control signals for branch not equal? Well, we're going to have register write 0. We don't want to write anything into the register file when we're doing a branch. For read, so ALU read source is going to be read data 2. So we want to take in both two registers here and want to compare them because we're doing branch not equal. We're not using the sign extension in the ALU. The ALU operation is going to be subtract because we want to see if they're different. And then the PC source here, what do we select? Well, we're going to select this ALU result, the branch address, if it is not 0, as it's a branch not equal. So we're going to select this one down here. We're going to do the branch if it's not 0. All right. Go ahead, pause the video, answer the question first on your own, then discuss with your partner. Okay, so why was a single branch output from the control logic not enough to handle both branch not equal and branch equal instructions? Well, the answer here is we need to interpret the ALU's 0 output differently for each. If we have a branch equals instruction, then when it's 0, that means they're the same, so it is a branch. But if it's branch not equal, we don't want to branch on the 0 because branch not equal, we should branch if they're not 0. So we need to know whether we interpret the 0 being true as we should branch or the 0 being true as we shouldn't branch, and we need a separate signal for that.